Before we begin, take a moment to settle into your bed, letting the weight of your body sink into the mattress. Close your eyes gently and allow the quiet of this moment to fill the space around you, as if the earth itself were breathing in sync with your own rhythm. Feel the air brushing softly across your skin and the faint pulse of your own heartbeat as we journey together through time, far into the distant future of our planet. What will the Earth look like millions of years from now, when the landscapes we know have transformed beyond recognition, when oceans and mountains have shifted and life itself has adapted to a world unrecognizable to our present eyes? In the span of geological time, the Earth is constantly reshaping, with forces moving far slower than a human lifetime, yet inexorably powerful. The continents, carried on massive tectonic plates, crawl across the globe, colliding, drifting apart, and merging over tens of millions of years. Today's familiar continents are but temporary arrangements in an endless cycle of formation and destruction. The movement of tectonic plates begins with the slow, almost imperceptible motion of the lithosphere atop the semi-fluid asthenosphere beneath. Each continental plate drifts at a pace measured in centimeters per year, yet over millions of years, this motion is sufficient to reshape entire ocean basins and form new mountain ranges. Scientists studying the history of supercontinents have observed cycles, each lasting hundreds of millions of years, where land masses converge into vast continents before dispersing once again. Millions of years from now, the Earth may witness the assembly of a new supercontinent, possibly taking a form that unites the Americas with Eurasia and Africa, creating enormous interior deserts and vast mountain chains far from any coast. These colossal transformations will redefine ocean currents, wind patterns, and climate zones across the globe. Alongside the slow drift of land, the Earth's climate will continue its long-term evolution. Over the next tens of millions of years, variations in Earth's orbit, axial tilt, and precession, collectively known as Milankovitch cycles, will alter the distribution of sunlight across the planet's surface. Such cycles have historically triggered ice ages and warmer interglacial periods, but future cycles will play out in combination with gradual increases in solar luminosity. As the sun slowly brightens over millions of years, global temperatures may rise, leading to the retreat of ice sheets and expansion of arid regions. Oceans will respond, shifting currents that distribute heat and nutrients, potentially causing shifts in marine ecosystems as certain species thrive and others decline. Life on Earth, resilient and adaptive, will continue to respond to these shifting environments. Ecosystems will reorganize as habitats migrate with the changing climate and the gradual reconfiguration of continents. Species that survive long-term climate pressures will evolve to exploit new ecological niches, while others will vanish entirely, leaving traces only in fossil records for future millennia to uncover. Microbial life, plants, and animals will all continue their relentless evolution, shaping a biosphere adapted to conditions far different from those experienced today. The interplay between evolving landscapes, climate, and life will create patterns of biodiversity both familiar and strange, dictated by the slow, steady forces of geology and physics. Rising and falling sea levels, influenced by both glacial cycles and tectonic movements, will continuously reshape coastlines. Vast continental shelves may submerge, forming shallow seas, rich with nutrients and life, while other regions rise above the water to become new land masses. Ocean chemistry will shift gradually as weathering of rocks and volcanic activity introduce minerals into the waters, while the balance of carbon dioxide, oxygen, and other gases fluctuates in response to biological activity and geophysical processes. Marine life will adapt to these changes, with coral reefs, plankton populations, and fish species all undergoing shifts in distribution and abundance over millions of years. Earth's atmosphere will also evolve. Over geological timescales, the concentrations of oxygen and carbon dioxide have varied dramatically, and future fluctuations are expected as tectonic activity, volcanism, and life continue to interact. Higher carbon dioxide levels may accelerate warming, while oxygen levels will support complex life as long as photosynthetic processes persist. The balance between greenhouse gases and atmospheric composition will shape the habitability of regions, influencing rainfall patterns, storm intensity, and the distribution of ecosystems. Even the highest mountains and the deepest valleys will experience these atmospheric effects as clouds gather, winds flow, and precipitation cycles continue uninterrupted for millions of years. In parallel, the sun's slow increase in luminosity will subtly alter life's potential on the surface. While the change is imperceptible on human timescales, over tens of millions of years, even a fractional increase in solar output will affect evaporation, precipitation, and the global energy balance. Tropical regions may expand, polar regions may shrink, and deserts may extend across vast expanses of interior continents. These changes will influence soil formation, vegetation distribution, and river dynamics, reshaping the surface of the planet in ways both gradual and profound. Rivers that once meandered lazily across flat plains may carve deeper valleys as rainfall and erosion patterns shift. The coasts of continents will recede or advance, responding to both tectonic uplift and changing ocean volumes, leaving behind a record of Earth's ongoing transformation in sediment layers and fossilized shorelines. Beneath the surface, the oceans will quietly record the passage of time, their depths hosting slow-moving currents and deep-sea ecosystems that have persisted for hundreds of millions of years. The chemistry of seawater will continue to evolve as minerals leach from newly exposed rocks and volcanic activity injects fresh elements into the marine environment. Nutrient cycles will adapt to these shifts, shaping the productivity of phytoplankton and, in turn, influencing the food chains of countless marine species. Hydrothermal vents on the seafloor will remain oases of life, providing energy and chemical compounds in the absence of sunlight, sustaining communities of extremophiles adapted to high temperatures and pressures. In deeper trenches, pressure-tolerant organisms will navigate a world largely unchanged in darkness, but slowly modified by sediment accumulation, tectonic uplift, and shifts in ocean chemistry. Meanwhile, the magnetic field of the Earth will continue its slow, irregular dance, generated by the convective motions of the liquid iron core. Over millions of years, the field will experience reversals and fluctuations, with periods of weaker intensity that could alter the planet's protection from solar and cosmic radiation. Life on the surface will experience these subtle shifts in radiation exposure, with evolutionary pressures favoring adaptations in DNA repair, reproductive strategies, and behavioral patterns. Paleomagnetic studies reveal that these processes are cyclical and natural, and future organisms will inherit a world where geomagnetic variations are part of the environmental landscape. Tectonic activity will persist as a dominant sculptor of the Earth's surface. Mountain ranges will rise as plates collide, erode as weathering takes its toll, and eventually sink beneath the weight of glaciers, rivers, and sediment accumulation. Volcanoes will continue to punctuate landscapes with fresh rock, altering local climates temporarily and contributing to long-term atmospheric carbon cycles. Valleys, plains, and high plateaus will shift subtly as Earth's crust responds to internal stresses, creating new drainage patterns, river networks, and sedimentary basins. These features, although imperceptible on daily timescales, accumulate over millions of years to create landscapes profoundly different from anything seen today. As supercontinents assemble and disperse, ocean basins will expand and contract in response. The closure of seaways may redirect global currents, creating warm equatorial gyres or polar bottlenecks, which in turn influence climate on a planetary scale. Some shallow seas may evaporate, leaving behind mineral-rich salt flats and sedimentary deposits that record these environmental extremes. Elsewhere, new seas may flood continental lowlands, establishing rich habitats for marine organisms. Ocean currents will adjust to these changes, affecting heat transport, nutrient upwelling, and biological productivity. Each cycle of ocean expansion and contraction will subtly influence the evolution of marine life, driving adaptation, migration, and occasionally extinction. The continents themselves, reshaped by collision and rifting, will host climates that shift from arid interiors to temperate coasts as mountain ranges block winds and redirect precipitation. Deserts may expand in the supercontinent interiors, where limited moisture and extreme temperatures dominate, while coastal margins benefit from moderated climates influenced by nearby oceans. Vegetation will follow these patterns, with hardy, drought-resistant species in arid interiors and lush forests along coastal zones. Soil composition will change gradually as minerals weather and organic matter accumulates, influencing which plants can thrive and shaping the habitats available for future animal life. Each plant community will play a role in stabilizing landscapes, moderating erosion, and cycling nutrients. In polar regions, ice sheets and glaciers will respond to the interplay of tectonics, solar output, and atmospheric composition. At times, massive ice sheets may cover northern and southern continents, carving valleys, depositing moraines, and altering sea levels worldwide. During warmer periods, these ice sheets may retreat, leaving behind glacial lakes and reshaped coastlines. The repeated advance and retreat of ice across millions of years will leave a subtle imprint on the geology, shaping topography and sediment patterns, and creating niches for species able to adapt to these extreme seasonal changes. Even in these frozen regions, microbial and specialized plant life will endure, continuing the persistent cycle of adaptation and survival. Volcanism, both on land and beneath the oceans, will continue to inject energy and matter into the Earth system. Lava flows, ash deposits, and hydrothermal vent activity contribute to mineral cycling, soil formation, and chemical diversity in aquatic and terrestrial environments. Over millions of years, volcanic regions may rise to form new islands, alter rainfall patterns locally, and create habitats for colonizing species. The slow accumulation of volcanic material and its interaction with erosion, wind, and precipitation will constantly reshape landscapes, contributing to the geological narrative recorded in rock layers across the planet. The interplay of these processes illustrates the dynamic, ever-changing nature of Earth, even when viewed through the slow lens of deep time. Throughout these transformations, Earth's atmosphere will continue its subtle evolution. Volcanic eruptions, tectonic degassing, and biological activity contribute to the balance of gases, influencing greenhouse warming and cooling cycles. Oxygen levels, critical for complex life, will fluctuate in response to photosynthetic activity, biomass decomposition, and ocean chemistry. Carbon dioxide, as both a greenhouse gas and a driver of ocean acidity, will guide long-term climate trends, influencing ice coverage, precipitation patterns, and the distribution of ecosystems. The atmosphere, seemingly invisible, will act as a gentle but persistent sculptor, shaping every living system and landscape over tens of millions of years. Over the coming millions of years, the chemistry of Earth's oceans will continue to shift, influenced by the slow dissolution of minerals from continental rocks, hydrothermal vents on the ocean floor, and the cycling of elements through living organisms. Nutrients, such as phosphorus, nitrogen, and trace metals, will accumulate in some regions and become depleted in others, guiding the productivity of marine ecosystems. Plankton populations, foundational to the food web, will respond to these variations, adapting to changing nutrient levels and light availability. Over long spans of time, entire marine communities will evolve in response, some flourishing in newly formed shallow seas, others adapting to extreme environments such as deep trenches or hypersaline lagoons created by shifting sea levels. The chemistry of seawater, although subtle in its daily influence, will quietly dictate which species thrive, migrate, or disappear, leaving behind a record in the sedimentary layers for future eons. Life on land will mirror the gradual but relentless changes of the oceans. As continents drift and climates shift, species will follow the movement of habitable zones. Forests may expand into previously barren regions, only to retreat when aridity or glaciation dominates. Grasslands may spread across temperate interiors, supporting a diverse array of herbivores and their predators. Evolution will act on both large and microscopic scales, with organisms refining their physiology, reproductive strategies, and behaviors to cope with altered temperatures, precipitation patterns, and soil compositions. Over millions of years, speciation will generate novel lineages, while extinction will prune those unable to adapt, resulting in an ever-changing tapestry of life, continuously rewritten by the interplay of environment and genetics. The long-term brightness of the sun will impose a subtle but persistent influence on these ecosystems. Over the next hundreds of millions of years, the sun will gradually increase in luminosity, raising global temperatures and intensifying evaporation rates. Polar ice may shrink, tropical regions may become warmer and more humid, and the distribution of deserts and fertile lands will slowly shift. Rivers will carve deeper valleys under changing precipitation regimes. Sediment will accumulate in new basins, and coastlines will advance or recede as sea levels respond to both thermal expansion and ice sheet dynamics. Life will track these slow environmental changes with migration patterns, growth cycles, and species distributions continually adapting to the evolving climate. Marine life will continue to respond to these environmental pressures, particularly in regions of high productivity such as coastal upwellings and nutrient-rich shallow seas. Coral reefs, if conditions permit, may expand or contract with temperature fluctuations and ocean chemistry, providing habitats for countless species of invertebrates and fish. Deep-sea ecosystems, largely insulated from surface changes, will maintain their slow pace of evolution, with microbial communities adapting to subtle chemical and thermal shifts over millions of years. Predatory and prey species will co-evolve, maintaining ecological balances within complex food webs that have persisted through countless geological epochs. Tectonic activity will continue to shape the oceans themselves. New mid-ocean ridges will emerge, generating fresh crust and slowly expanding the sea floor, while subduction zones will consume older lithosphere, drawing ocean basins toward closure and driving the formation of future supercontinents. These processes will alter the depth, volume, and circulation of the oceans, with cascading effects on climate and marine life. The oceans, ever dynamic, will carry the story of Earth's changing surface, recording in sediment layers and chemical gradients the gradual unfolding of planetary history. Volcanic activity, particularly under the oceans, will contribute to both chemical enrichment and habitat formation. Lava flows will create new islands and undersea mountains, while the release of gases such as carbon dioxide and sulfur dioxide will influence local and global climate conditions. Hydrothermal vent systems will remain hotspots of chemical energy, supporting unique communities of organisms adapted to high temperatures and chemical gradients. These vents, persistent over millions of years, will act as refuges and incubators for life during periods when surface conditions become less hospitable, ensuring continuity in Earth's biosphere. The interplay of solar radiation, atmospheric composition, and tectonic shifts will gradually redefine the boundaries of habitable zones. Equatorial regions may experience higher temperatures and more intense rainfall, fostering dense vegetation, while mid-latitudes fluctuate between temperate and semi-arid conditions. The slow changes in sunlight, angle, day length, and seasonal patterns will continue to influence migration, breeding cycles, and ecological interactions. Life on Earth will persist not as a static panorama, but as a continuously adjusting network of organisms responding to the dynamic equilibrium imposed by planetary processes. Over tens of millions of years, Earth's surface will bear the cumulative effects of erosion, sedimentation, and tectonic uplift. Mountain ranges will slowly wear down, rivers will carry sediment to new basins, and plains will shift under the weight of accumulated soil and organic material. The interaction of these forces with evolving climates and ecosystems will produce landscapes that are familiar in structure, but fundamentally transformed in composition and distribution. Even the most stable regions of continental interiors will record subtle changes in rock formations, soil chemistry, and hydrology, chronicling the invisible but persistent work of geologic time. In parallel, Earth's magnetic field will continue its long-term fluctuations, including reversals of polarity and variations in field strength. These changes, although imperceptible on human timescales, will influence the distribution of charged particles from the solar wind, slightly altering surface radiation levels. Life will adapt accordingly, with species developing strategies to cope with the intermittent increases in radiation exposure. The magnetic field, a protective yet fluctuating barrier, is one of many subtle forces guiding the evolution of the biosphere over millions of years. shaping life quietly but persistently across generations. As millions of years unfold, the gradual motion of tectonic plates will bring the continents into configurations that may culminate in the formation of a new supercontinent. Geologists have proposed several scenarios based on the direction and speed of current plate movements, in which landmasses such as Africa, the Americas, Eurasia, and Australia converge once again. The resulting supercontinent will create extensive interior regions far from the moderating influence of oceans, giving rise to vast deserts and extreme temperature ranges. These arid interiors may experience scorching summers and freezing winters, with limited water availability shaping the evolution of plants and animals capable of surviving under such harsh conditions. Rivers that originate in distant mountain ranges may traverse great continental distances, carving valleys, depositing sediments, and creating oases along their courses, while many smaller streams may vanish into arid plains, their waters evaporating before reaching any sea. Coastal regions will present a stark contrast to the interior, where ocean currents and prevailing winds bring moisture and temperate climates. Tidal patterns, driven by the moon's gravitational influence, will continue to shape shorelines, erode cliffs, and deposit sands along expanding beaches. Rising or falling sea levels, influenced by glacial cycles and thermal expansion, will alternately submerge coastal plains and expose new areas of land, allowing ecosystems to expand or retract in response. Mangroves, marshes, and shallow marine habitats may flourish where nutrient-rich waters mix with sediment-laden rivers, forming productive zones that support a variety of life forms adapted to fluctuating water levels. In extreme climates, such as polar regions, the interplay between glacial growth and retreat will shape the landscape over millions of years. Ice sheets will advance across continents during cooler periods, gouging valleys, depositing moraines, and compressing sediment beneath their immense weight. When temperatures rise, these ice sheets will retreat, releasing meltwater into rivers, lakes, and oceans, and sculpting U-shaped valleys and fjords along the way. Glacial cycles, repeating over tens of millions of years, will leave an indelible mark on topography, influencing soil distribution, vegetation patterns, and habitats for both terrestrial and aquatic life. Even in periods of maximum glaciation, microbial life, lichens, and cold-adapted organisms will persist, demonstrating the resilience of life to climatic extremes. Long-term atmospheric trends will continue to guide the Earth's climate and habitability. The composition of gases such as carbon dioxide, methane, and oxygen will fluctuate in response to volcanic activity, weathering, and biological processes. Over millions of years, these fluctuations may lead to intervals of enhanced greenhouse warming or gradual cooling. Volcanic eruptions will release both heat-trapping gases and aerosols, temporarily cooling the surface while contributing to long-term shifts in carbon cycles. Photosynthetic life, particularly in oceans, will continue to influence atmospheric oxygen and carbon dioxide levels, maintaining the delicate balance required for complex life forms to persist. Ocean circulation patterns will evolve in response to the shifting positions of continents and the changing depth of ocean basins. Closure of seaways and the formation of new channels may redirect currents, affecting the transport of heat from equatorial regions toward the poles. These adjustments will influence climate zones across continents, determining the distribution of deserts, forests, and wetlands. Upwelling zones, where nutrient-rich waters rise from the deep, will shift locations, altering primary productivity and the abundance of marine organisms dependent on planktonic food sources. Over geological timescales, these patterns will be reflected in sediment deposits, fossil distributions, and the chemical signatures preserved in marine sediments. Mountain ranges formed by continental collisions will continue to rise and erode, creating new habitats and influencing regional climate. High elevations will experience cooler temperatures and increased precipitation, supporting alpine ecosystems that may differ significantly from lowland forests and plains. Rivers originating in mountains will carve valleys and transport sediment to coastal areas, affecting delta formation and the nutrient content of adjacent seas. As erosion gradually wears down peaks over millions of years, sediment will accumulate in basins, contributing to fertile soils that support terrestrial ecosystems capable of sustaining a variety of life forms. The biosphere will continually adapt to these long-term changes. Species will shift their ranges in response to climatic and geographic transformations, migrating towards suitable habitats, evolving to exploit new ecological niches, or facing extinction when adaptation is insufficient. Plant communities will reorganize as soils change in composition and moisture retention, influencing herbivore populations and cascading through food webs. Predatory species will follow prey migrations, while symbiotic relationships evolve in response to environmental pressures. Over millions of years, these processes will create a dynamic equilibrium in which life persists despite constant transformation, maintaining the continuity of ecological networks across geological epochs. In the oceans, chemical changes resulting from tectonic activity and biological processes will guide the evolution of marine ecosystems. Acidification levels will fluctuate as carbon dioxide dissolves into seawater, affecting calcifying organisms such as corals and shellfish. Nutrient availability will vary as currents shift and continental weathering delivers minerals to coastal regions. Deep-sea ecosystems, insulated from surface fluctuations, will adapt slowly to these changes, maintaining specialized communities around hydrothermal vents and cold seeps. Surface and shallow water organisms will experience more rapid evolutionary pressures, leading to cycles of adaptation and selective extinction that mirror those occurring on land. As the sun continues its slow increase in luminosity, equatorial regions may experience higher temperatures, enhancing evaporation rates and driving the expansion of tropical forests, savannas, and monsoon systems. Polar regions, although warming, will retain glacial refuges where cold-adapted species can survive. Seasonal cycles will persist, but day length, solar angle, and precipitation patterns will gradually shift over millions of years, subtly influencing reproductive timing, migration, and ecological interactions. Life on Earth, both terrestrial and marine, will continue to adapt to these persistent but gentle forces, creating a world that is recognizably alive, yet fundamentally altered from the landscapes known today. Over tens of millions of years, the Earth's tectonic plates will continue their relentless motion, altering the shapes and positions of continents and ocean basins. Subduction zones will consume older oceanic crust, recycling it into the mantle and generating volcanic arcs that punctuate coastlines with fresh rock and fertile soils. Mid-ocean ridges will steadily create new seafloor, widening oceans in some areas even as others shrink. These changes will influence the circulation of ocean currents, which carry heat, nutrients, and gases across the planet. Shifts in current patterns will affect climate on both regional and global scales, redistributing rainfall, influencing the formation of deserts and wetlands, and altering the productivity of both terrestrial and marine ecosystems. Ocean chemistry will respond subtly to these tectonic and climatic forces. Minerals released from eroding mountains will flow into rivers and eventually reach the seas, altering the concentrations of elements such as calcium, magnesium, and silica. These changes will impact organisms that rely on mineral deposition, from shell-building mollusks to reef-forming corals. Phytoplankton, the primary producers of the oceans, will continue to adapt to fluctuations in nutrient availability, their populations influencing the abundance and distribution of larger species. Deep-sea ecosystems, largely insulated from surface changes, will remain remarkably stable, yet even they will slowly respond to the gradual redistribution of chemical elements and variations in hydrothermal activity. Life on land will also reflect the interplay of tectonics, climate, and atmospheric composition. As continents collide and mountains rise, rain shadows will create dry interior regions, while coastal slopes experience higher precipitation. Plant communities will reorganize in response to these gradients, with drought-tolerant species dominating arid interiors and moisture-dependent species flourishing in temperate and tropical regions. Herbivorous animals will migrate to follow suitable forage. Predators will track their prey, and symbiotic relationships will evolve over millions of years. Extinction events, driven by climatic extremes, volcanic eruptions, or habitat changes, will be counterbalanced by speciation and adaptation, resulting in a continuously shifting mosaic of biodiversity across continents. Volcanism will continue to play a significant role in shaping both land and atmosphere. Large eruptions will inject ash and gases into the atmosphere, temporarily cooling surface temperatures and modifying precipitation patterns. Over long timescales, volcanic carbon dioxide emissions will contribute to greenhouse warming, influencing the global climate and interacting with the slow brightening of the sun. Lava flows and pyroclastic deposits will create new landforms, altering drainage patterns, soil composition, and the distribution of habitats. Islands formed by volcanic activity may provide isolated refuges for life, enabling unique evolutionary pathways that persist over millions of years. Ice dynamics will persist in polar regions, responding to the balance between solar radiation, atmospheric composition, and oceanic currents. Glacial advance and retreat will sculpt valleys, carve fjords, and redistribute sediments across continents. Meltwater will contribute to sea level fluctuations, impacting coastal ecosystems and sediment deposition patterns. Even small changes in glaciation will influence global climate by altering albedo, which affects the reflection of sunlight and the absorption of heat. The persistence of ice, despite long-term warming trends, will provide refuge for cold-adapted species and maintain critical components of Earth's hydrological cycle. The gradual increase in solar luminosity will have a subtle yet persistent influence over millions of years. Equatorial regions may become warmer and more humid, intensifying rainfall and supporting expansive tropical forests and monsoon systems. Mid-latitudes may experience shifts between temperate and semi-arid conditions, influencing the migration of plant and animal populations. Polar regions, while warming, may retain pockets of glacial ice that act as refuges for specialized species. The long-term brightening of the sun will amplify the effects of greenhouse gases, gradually reshaping the boundaries of habitable zones and imposing a slow but inexorable pressure on both terrestrial and marine ecosystems. Atmospheric composition will continue its delicate evolution. Carbon dioxide, oxygen, and nitrogen levels will fluctuate in response to volcanic degassing, weathering, and biological activity. Periods of elevated greenhouse gases will intensify warming, while intervals of lower concentrations may trigger cooler climates and glacial expansion. Photosynthetic organisms, from terrestrial plants to oceanic phytoplankton, will regulate oxygen levels and contribute to carbon cycling, maintaining the atmosphere's capacity to support complex life. The interplay of gas concentrations, temperature, and precipitation will define the long-term habitability of different regions, guiding the evolution of life and the distribution of ecosystems over geological timescales. Throughout these millions of years, Earth's landscapes will continue to be sculpted by erosion, sedimentation, and tectonic uplift. Mountain ranges will rise and wear down. Rivers will carve valleys and deposit sediment in deltas and basins, and plains will gradually shift under the accumulation of soil and organic matter. The interaction of these processes with climate, ocean currents, and biological activity will generate a dynamic, ever-changing surface. Even the most stable regions will experience subtle transformations, reflecting the cumulative effects of geologic and environmental forces acting over vast spans of time. Beneath the surface of the oceans, life will continue its patient evolution, responding to changes in chemistry, temperature, and circulation patterns. Deep-sea environments, insulated from the dramatic fluctuations of surface waters, will maintain relatively stable conditions, supporting communities of specialized organisms. Hydrothermal vent systems will persist as oases of chemical energy, hosting bacteria and archaea that convert minerals into life-sustaining compounds. Over millions of years, these communities will gradually diversify, some species adapting to subtle changes in vent activity, while others spread along ocean ridges and seamounts. The slow accumulation of sediment around these habitats will preserve a record of biological activity, chronicling the evolution of organisms in a world largely hidden from sunlight. Surface marine ecosystems will experience more pronounced changes. Coral reefs, plankton blooms, and coastal ecosystems will respond to shifts in ocean temperature, chemistry, and nutrient availability. Regions of upwelling will continue to provide nutrient-rich waters, supporting large populations of fish and invertebrates, while oligotrophic regions may see declines in productivity. Ocean acidification, driven by fluctuating carbon dioxide levels, will challenge calcifying organisms, prompting evolutionary adaptations or local extinctions. Over millions of years, these processes will restructure marine food webs, shaping the distribution, abundance, and diversity of species across the globe. On land, plant life will follow patterns dictated by climate, soil composition, and water availability. Forests, grasslands, and shrublands will reorganize in response to changing precipitation, temperature, and nutrient distribution. Drought-tolerant species will dominate arid interiors of future supercontinents, while moisture-dependent species will flourish along coasts and river valleys. Photosynthetic organisms will regulate atmospheric oxygen and carbon dioxide, influencing climate and sustaining complex terrestrial ecosystems. Over geological timescales, species will emerge, adapt, and disappear, leaving traces in fossil layers that chronicle the long-term interplay of life and environment. Animal populations will continue to migrate, adapt, and evolve in response to shifting landscapes and climates. Herbivores will track plant availability, predators will follow prey migrations, and symbiotic relationships will adjust to new ecological contexts. Isolated habitats, such as islands formed by volcanic activity or glacial refuges in polar regions, will allow unique evolutionary paths, resulting in localized speciation. Extinction events, whether driven by climate extremes, volcanic eruptions, or habitat loss, will be counterbalanced by the emergence of new species, maintaining the dynamic equilibrium of ecosystems over millions of years. Sea levels will fluctuate in response to glaciation, tectonics, and thermal expansion. Shallow continental shelves may be periodically submerged or exposed, creating transient habitats for marine and coastal organisms. Sediment deposition in these regions will enrich soils, support vegetation, and provide nutrients to adjacent waters. Estuaries, deltas, and lagoons will form and dissipate, offering zones of high productivity and ecological diversity. These changes, though gradual over human timescales, will continually redefine habitats and influence evolutionary trajectories in both terrestrial and marine ecosystems. Volcanic activity will continue to shape both the land and the oceans. Subaerial eruptions will create new mountains and fertile plains, while submarine volcanism will build islands and seamounts. The release of gases, including carbon dioxide and sulfur compounds, will modulate climate, affecting temperatures, rainfall patterns, and atmospheric chemistry. Lava flows and ash deposits will interact with erosion, wind, and precipitation to form landscapes that are ever-changing yet persistently molded by the interplay of geological forces. Volcanic regions will act as both hazards and opportunities for life, providing new substrates for colonization and habitats that support adaptive evolution. The gradual brightening of the sun will subtly influence every ecosystem. Increased solar radiation will elevate temperatures in equatorial regions, expanding tropical forests and enhancing evaporation and rainfall. Mid-latitudes may experience periods of semi-aridity, shaping the distribution of grasslands, savannas, and deserts. Polar regions, although warming, will retain glacial refuges, preserving ecosystems adapted to cold conditions. This slow but persistent change in solar output will guide the evolution of life, imposing constraints that encourage adaptation, migration, and diversification over millions of years. Atmospheric dynamics will continue to interact with these physical and biological processes. Fluctuations in carbon dioxide, methane, and oxygen will influence greenhouse warming, ice sheet formation, and precipitation cycles. Periods of elevated greenhouse gases may lead to higher temperatures and sea level rise, while intervals of lower concentrations could trigger cooler climates and glaciation. Photosynthetic organisms, through their role in regulating atmospheric composition, will help stabilize conditions conducive to complex life. Clouds, winds, and precipitation will continue to shape the surface, redistributing water, nutrients, and energy across ecosystems, subtly guiding the long-term evolution of life and landscapes. Earth's magnetic field will maintain its slow, unpredictable fluctuations, including polarity reversals and variations in field strength. While largely imperceptible to the organisms on the surface, these changes influence the shielding of solar and cosmic radiation, creating intermittent variations in radiation exposure. Over geological timescales, life will adjust to these fluctuations, with adaptations in DNA repair mechanisms, reproductive strategies, and behavior contributing to survival in an environment where even subtle forces play a continuous role in shaping evolutionary trajectories. Sedimentary processes will continue to record the history of Earth's surface. Rivers will transport sediments from mountains to oceans. Wind will carry fine particles across continents, and glaciers will grind bedrock into soils and sediments. These deposits will accumulate in layers, preserving fossils, chemical signatures, and mineral compositions that reveal the slow transformation of landscapes, oceans, and ecosystems. Over millions of years, this geologic record will capture the dynamic interactions of tectonics, climate, life, and solar influence, providing a chronicle of Earth's long-term evolution that spans the distant future. As the continents continue their slow dance across the globe, ocean circulation patterns will be continually reshaped. The opening and closure of seaways will redirect major currents, altering the distribution of heat and nutrients across both surface and deep waters. Warm equatorial waters may be channeled toward polar regions, enhancing melting at the edges of ice sheets, while nutrient-rich upwelling zones shift to new locations, sustaining bursts of primary productivity that support complex food webs. Over millions of years, these subtle adjustments will influence not only the abundance of marine species, but also their geographic distribution, as organisms follow favorable conditions or adapt to localized changes in temperature, salinity, and oxygen levels. In the interiors of future supercontinents, the climate will evolve under the influence of vast distances from the moderating oceans. Aridity may dominate, creating deserts that expand across hundreds or even thousands of kilometers, punctuated by isolated oases formed by river systems or glacial meltwater. Temperature extremes between day and night, summer and winter, will challenge the organisms that inhabit these regions. Plant species will evolve traits to conserve water, resist heat, or survive periods of dormancy, while herbivores and predators adapt to sparse and fluctuating resources. Soil development will be slow but steady, with mineral content influenced by the slow erosion of distant mountains and occasional volcanic ash deposits enriching fertility in localized areas. Coastal margins, in contrast, will experience moderated climates shaped by prevailing winds, ocean currents, and tidal forces. Wetlands, estuaries, and deltas will serve as hubs of biodiversity, supporting dense plant growth and a wide range of terrestrial and aquatic organisms. Seasonal variations will continue to drive reproductive cycles, migration patterns, and ecological interactions, maintaining dynamic yet balanced ecosystems. Over millions of years, as sea levels rise and fall in response to glaciation and thermal expansion, coastal habitats will continually reorganize, providing both challenges and opportunities for life to adapt. Mountain ranges will continue to shape local and regional climates. Their elevation will influence precipitation, with windward slopes receiving abundant rainfall while leeward slopes lie in rain shadows. These gradients will foster diverse habitats, from alpine meadows to temperate forests, each with its own assemblage of plants and animals. Rivers originating in these highlands will transport sediments to valleys and coasts, influencing soil fertility, delta formation, and the availability of freshwater habitats. Over long timescales, the erosion of mountains will redistribute materials across continents, altering landscapes and providing the foundation for new ecosystems to emerge. Volcanic activity will intermittently reshape land and ocean habitats. Submarine eruptions will create new seamounts and islands, serving as isolated habitats for colonizing species. Subaerial eruptions will inject ash and gases into the atmosphere, influencing climate temporarily and modifying soil composition over longer periods. Lava flows will create new topography, while ash deposits will enrich soils, enabling plant colonization and succession. These processes, slow and measured over millions of years, will create new ecological opportunities while simultaneously imposing environmental pressures that drive evolution. The biosphere will continue its unbroken adaptation to these shifting landscapes and climates. Terrestrial species will migrate to track suitable habitats, evolve traits that allow them to survive in new conditions, or face extinction when adaptation is insufficient. Aquatic species will similarly respond to changing currents, nutrient availability, and water chemistry. Evolutionary pressures will favor those organisms capable of flexibility, efficiency, and resilience. Over millions of years, ecosystems will reorganize repeatedly, but life, in its myriad forms, will persist, leaving traces in both sediments and rock formations that capture the story of adaptation and survival. Sea levels will fluctuate with glacial cycles, tectonic uplift, and thermal expansion. Shallow seas may form over continental interiors, creating temporary habitats for marine life and influencing sediment deposition. Coastal zones will experience periods of expansion and contraction, influencing the distribution of intertidal species, mangroves, and estuarine ecosystems. Sediments carried by rivers and glaciers will enrich soils and coastal waters, maintaining productivity and supporting complex food webs. Over millions of years, these processes will gradually reshape coastlines, leaving behind layers of sediment that chronicle the interplay of land, sea, and life. The sun's gradual brightening will continue to influence global climates and ecological patterns. Equatorial regions may see increased rainfall and expansion of tropical forests, while mid-latitudes experience shifting zones of semi-aridity and grassland. Polar regions, though slowly warming, may retain pockets of ice that act as refuges for cold-adapted species. Seasonal cycles, day length, and solar angles will shift imperceptibly but inexorably, subtly guiding the timing of reproduction, migration, and plant growth. Life on Earth will continue to track these changes, evolving in harmony with the slow rhythm of planetary and solar transformations. Atmospheric composition will remain a critical regulator of climate and habitability. Volcanic emissions, weathering, and photosynthetic activity will influence concentrations of carbon dioxide, oxygen, and nitrogen. Fluctuations in these gases will dictate greenhouse warming, glacial expansion, and precipitation patterns. Over millions of years, the balance between carbon sources and sinks will shape global temperature trends, influencing which regions remain hospitable to life and which become inhospitable deserts or glacial zones. Photosynthetic organisms will maintain the oxygen content of the atmosphere, ensuring the continued viability of complex life forms and sustaining the intricate web of ecosystems across continents and oceans. Even as landscapes, climates, and oceans shift, the magnetic field will continue to fluctuate, protecting the biosphere from cosmic and solar radiation in varying degrees. Polarity reversals and periods of weaker field intensity may briefly increase exposure, but life will adapt to these conditions, maintaining the continuity of ecosystems. Sedimentary deposits, fossil records, and chemical markers will accumulate over millions of years, providing a detailed archive of Earth's evolving surface. The passage of time and the resilience of life in the face of constant planetary transformation. Over millions of years, the interiors of future supercontinents will evolve into expansive, arid landscapes, shaped by their distance from oceans and the subtle interplay of topography and climate. Deserts will gradually expand, punctuated by seasonal or permanent rivers that carve valleys, create oases, and deposit fertile sediments in otherwise barren regions. Wind patterns will transport fine dust and mineral particles across vast distances, enriching soils in some areas while accelerating erosion in others. These continental interiors will experience extreme temperature fluctuations between day and night and across seasons, challenging organisms to develop specialized adaptations, from water storage in plants to behavioral strategies in animals that minimize heat stress or conserve moisture. Isolated habitats within these interiors, such as river valleys or glacial refuges in mountainous regions, will act as sanctuaries for species unable to tolerate the surrounding extremes. These refuges will foster unique evolutionary pathways as populations adapt to localized conditions over millions of years. Glacial meltwater will provide a consistent source of fresh water in some valleys, maintaining small but persistent ecosystems, while periodic flooding will rejuvenate soils and deposit nutrients transported from distant highlands. Such cycles of scarcity and abundance will guide evolutionary pressures, shaping species capable of resilience and long-term survival in harsh interior environments. Desertification cycles, though gradual, will have profound effects on biodiversity and sedimentary processes. Sand dunes will migrate across the landscape, occasionally burying vegetation or altering river courses. Soil crusts stabilized by microbial and fungal communities will develop in some regions, moderating erosion and supporting sparse plant life. Over geological timescales, the shifting balance between desert expansion and the retreat of arid zones during wetter periods will sculpt the surface, leaving behind patterns preserved in sediments that reflect these slow but persistent environmental changes. Coastal regions, in contrast, will maintain more temperate and productive ecosystems, responding to sea level fluctuations, tidal forces, and nutrient inputs from rivers. Estuaries, deltas, and marshlands will support dense communities of plants, invertebrates, and fish, providing crucial links between terrestrial and marine ecosystems. Sea level rise and fall, driven by glacial melting and thermal expansion, will cyclically expand and contract these habitats, creating opportunities for colonization, adaptation, and the reorganization of ecological networks over millions of years. Sediment deposition from rivers will enrich these areas, ensuring the persistence of fertile soils and productive waters that sustain life despite global shifts in climate and geography. Glacial refuges in high latitudes and mountainous regions will persist as cold-adapted ecosystems, even as equatorial and mid-latitude zones gradually warm. ice sheets will advance and retreat over millennia, carving valleys, forming lakes, and influencing river patterns. Microbial life, lichens, and hardy plants will survive at the margins of glaciers, while cold-tolerant animals will find sanctuary in these regions. These refuges will act as reservoirs of biodiversity, preserving lineages that may later expand when climates allow. Over tens of millions of years, glacial cycles will leave behind characteristic landforms, including U-shaped valleys, moraines, and sediment deposits, each recording the slow and persistent work of ice on the landscape. Biogeochemical feedbacks will subtly but continuously influence both climate and life. The erosion of mountains and the weathering of rocks will release minerals into rivers and oceans, supporting primary productivity and driving nutrient cycles. Photosynthetic organisms will regulate atmospheric oxygen and carbon dioxide, while decomposition and soil formation will recycle nutrients within terrestrial ecosystems. Carbon sequestration in soils, peatlands, and sediments will interact with volcanic degassing and tectonic activity, modulating greenhouse warming and cooling trends. These feedbacks, operating over millions of years, will maintain a dynamic equilibrium that allows life to persist in the face of slow but inexorable planetary change. Volcanic activity, both on land and beneath the oceans, will continue to reshape habitats and influence climate. Submarine eruptions will create new seamounts and islands, providing opportunities for colonization, while subaerial eruptions will modify soil chemistry, create fertile plains, and inject gases into the atmosphere that temporarily affect temperature and precipitation patterns. Lava flows and ash deposits will influence drainage patterns, river courses, and soil fertility, guiding the distribution of plant communities and the animals that depend on them. Over long timescales, these processes will subtly reshape ecosystems, creating new evolutionary opportunities and challenges. The sun's gradual brightening will persist as a subtle, constant influence. Equatorial regions will experience higher temperatures and increased evaporation, intensifying monsoons and supporting the expansion of tropical forests and savannas. Mid-latitudes will fluctuate between semi-arid grasslands and temperate forests, while polar regions retain pockets of glacial ice that preserve cold-adapted species. Seasonal and diurnal cycles will continue to shift imperceptibly over millions of years, subtly influencing reproductive timing, migration, and growth cycles. Life on Earth will track these changes, evolving adaptations that allow survival within the slowly altering climatic envelope. Oceanic currents and nutrient distribution will remain crucial for marine life. The configuration of continents and seaways will influence the path of warm and cold currents, affecting regional climates and the availability of nutrients. Upwelling zones will continue to deliver nutrient-rich waters to surface ecosystems, supporting phytoplankton blooms that form the foundation of marine food webs. Over millions of years, the interplay of currents, nutrient cycling, and chemical gradients will dictate the distribution of marine species, guiding evolutionary pressures in the oceans in parallel with terrestrial adaptation. Over tens of millions of years, life on Earth will continue to respond to the cumulative effects of climate, tectonics, and solar radiation. Terrestrial species will evolve to tolerate increasingly extreme conditions in arid interiors, adapting strategies for water conservation, thermoregulation, and efficient resource use. Plants may develop deep root systems to reach subterranean water, thickened leaves to minimize evaporation, and chemical defenses to deter herbivory in nutrient-poor soils. Animals will evolve behavioral, physiological, and anatomical traits that allow survival under fluctuating temperatures, scarce food supplies, and shifting habitats. These adaptations will unfold over countless generations, shaping lineages in ways that are slow, subtle, and deeply responsive to the surrounding environment. Coastal and marine ecosystems will reflect the interplay of fluctuating sea levels, nutrient availability, and climate change. Mangroves, estuaries, and coral reefs will expand or contract depending on the balance of sediment deposition, water temperature, and acidity. Phytoplankton populations will continue to respond to shifts in upwelling currents, influencing the abundance and diversity of fish and larger marine predators. In deeper waters, slow-evolving communities around hydrothermal vents and cold seeps will persist, serving as reservoirs of biodiversity that maintain continuity even as surface ecosystems fluctuate. Over geological timescales, these interactions between biology and environment will create complex, layered ecosystems that demonstrate both resilience and adaptability. Sedimentary processes will chronicle the changes occurring across the planet. Rivers will transport minerals and organic matter from mountains to oceans, depositing layers of sand, silt, and clay in deltas, basins, and coastal plains. Glacial activity will grind rocks into fine sediments, carving valleys and depositing moraines across landscapes. Wind will move fine dust and particles across deserts and plains, creating loess deposits and enriching soils far from their source. These sedimentary layers will record the gradual evolution of landscapes, the migration of species, and the chemical composition of oceans and atmosphere, preserving an archive of Earth's long-term transformation for future millennia. Glacial refuges and polar ecosystems will continue to serve as sanctuaries for cold-adapted life. Ice sheets will advance and retreat with long-term climatic cycles, sculpting U-shaped valleys, fjords, and moraines that will become permanent features of the landscape. Microbial life, lichens, and hardy plants will persist along glacial margins, while cold-adapted animals utilize these regions for breeding, foraging, and shelter. Even as equatorial and mid-latitude zones warm, these refuges will ensure the preservation of lineages that can recolonize other areas when conditions permit, maintaining continuity and diversity across the biosphere. The interplay between tectonics and climate will continue to influence evolution. Mountain-building events will alter wind and precipitation patterns, creating localized microclimates that harbor unique ecosystems. Volcanic eruptions will periodically modify habitats, releasing gases that influence climate, depositing minerals that enrich soils, and forming new landforms that serve as evolutionary testing grounds. These interactions, operating over millions of years, will continuously restructure habitats, drive adaptation, and select for traits that allow survival in a planet of shifting environmental conditions. Oceans will remain dynamic forces in shaping life and climate. Changes in ocean chemistry, temperature gradients, and circulation patterns will guide the distribution and evolution of marine species. Deep-sea currents will transport nutrients and dissolved gases across vast distances, sustaining life even in the most remote regions. Shallow coastal waters will experience cyclical periods of expansion and contraction, influenced by glacial cycles and sea level changes, creating ephemeral habitats that species exploit for feeding, breeding, and dispersal. These processes, gradual yet persistent, will structure marine ecosystems and ensure their continual adaptation over millions of years. The sun's increasing brightness will continue to exert subtle pressures on life and climate. Equatorial regions may become warmer and more humid, influencing rainfall patterns and the distribution of tropical forests. Mid-latitudes will shift between semi-arid and temperate conditions, shaping the composition and extent of grasslands, savannas, and forests. Polar regions will retain glacial ice, acting as refuges for cold-adapted species. Seasonal cycles, day length, and solar angles will evolve imperceptibly, guiding reproductive timing, migration, and growth patterns in both terrestrial and marine organisms. Life on Earth will persist, continually adjusting to these slow but unyielding solar influences. Atmospheric composition will remain a crucial regulator of habitability. Carbon dioxide, oxygen, and nitrogen levels will fluctuate in response to volcanic activity, weathering, and biological processes. Periods of elevated greenhouse gases may trigger warmer climates and higher sea levels, while intervals of lower concentrations may promote cooling and glaciation. Photosynthetic organisms will continue to modulate oxygen and carbon dioxide, maintaining conditions suitable for complex life. Clouds, winds, and precipitation will redistribute energy and nutrients across continents and oceans, guiding long-term ecological interactions and evolutionary trajectories. Finally, the accumulation of sediments and fossilized organic material will preserve an enduring record of these processes. Layers of rock will chronicle mountain uplift and erosion, glacial advance and retreat, desertification cycles, oceanic shifts, and the evolution of countless species. Chemical signatures within these layers will reveal changes in ocean acidity, atmospheric composition, and climate over millions of years. Fossil records will capture the forms of life that adapted, thrived, or vanished, providing a continuous archive of Earth's slow, measured transformation. The planet, in every grain of sediment, every fossilized leaf or shell, will retain the memory of eons of change, illustrating the profound resilience and adaptability of life in the face of continual planetary evolution. Over the next tens of millions of years, ecosystems across the globe will continue their slow evolution, shaped by the interplay of climate, geography, and biogeochemical cycles. In continental interiors, deserts and semi-arid regions will dominate vast stretches of land, yet life will persist through finely tuned adaptations. Plants will develop deeper root systems, thickened or waxy leaves, and water storage tissues to survive long dry seasons, while small mammals, reptiles, and insects will adapt behaviors and metabolic processes to endure scarcity and heat. Intermittent rivers and oases will become vital lifelines, supporting complex food webs that cycle energy and nutrients through these otherwise harsh environments. Over millennia, even sparse vegetation will contribute to soil formation and nutrient retention, gradually stabilizing these landscapes and allowing life to persist. In coastal regions, the constant exchange between land and sea will create productive and resilient ecosystems. Mangroves and salt marshes will thrive in tidal zones, filtering sediments and protecting shorelines from erosion, while providing habitats for fish, crustaceans, and migratory birds. Deltas formed by the deposition of river sediments will become centers of biological productivity, their soils enriched with minerals and organic matter. Coral reefs, where conditions allow, will continue to provide habitat complexity that supports immense biodiversity. Shifts in sea level and ocean chemistry, coupled with variations in temperature, will challenge these ecosystems, but selective adaptation will allow the most resilient species to persist, creating long-term stability despite environmental fluctuations. Nutrient cycling will remain a central process linking terrestrial and marine ecosystems. Weathering of rocks will release essential minerals into rivers, which will transport them to oceans, where planktonic organisms utilize them for growth. Decomposition on land and in shallow waters will return nutrients to the soil and sediments, maintaining productivity in a planet of ever-shifting climates and landscapes. Carbon, nitrogen, and phosphorus cycles will continue to regulate energy flow and ecosystem function, balancing greenhouse gas concentrations and sustaining habitable conditions over millions of years. These slow but persistent cycles will form the backbone of life's continuity, ensuring that ecosystems can adapt and recover from disturbances across geological timescales. Mountain ranges will continue to influence regional climates and ecological distribution. Elevation gradients will create distinct microclimates, with windward slopes receiving higher precipitation and supporting forests or alpine meadows, while leeward slopes experience rain shadows, giving rise to semi-arid valleys and grasslands. Rivers originating from these highlands will sculpt valleys, transport sediments, and maintain freshwater habitats for terrestrial and aquatic species. Erosion will slowly redistribute minerals across continents, enhancing soil fertility and sustaining life in downstream ecosystems. Over millions of years, these processes will generate diverse landscapes, each with its own assemblage of organisms adapted to local conditions. Glacial and polar regions will maintain critical refuges for life, even as global temperatures rise. Ice sheets will advance and retreat with climatic cycles, carving the terrain, forming lakes, and shaping river courses. Organisms adapted to cold, nutrient-rich environments will continue to persist in these isolated zones, acting as reservoirs of biodiversity that may recolonize temperate and subpolar regions when conditions permit. The persistence of these refuges will illustrate the resilience of life, demonstrating how species endure extreme conditions over geological timescales. Volcanic activity will periodically reshape the planet's surface, influencing climate, soil composition, and ecosystem dynamics. Lava flows, ash deposits, and the release of gases will create both challenges and opportunities for life. New substrates will provide space for colonization, while enriched soils will foster plant growth. Atmospheric effects from volcanic emissions, including temporary cooling or long-term greenhouse warming, will interact with other environmental factors to subtly influence regional and global climates. Life on Earth will respond to these episodic events with gradual adaptation, migration, and selective survival, maintaining continuity across generations. As the sun slowly brightens, equatorial regions may see expanded tropical forests and intensified rainfall, while mid-latitudes experience alternating periods of semi-aridity and temperate climates. Polar regions, retaining glacial refuges, will host cold-adapted species, while seasonal shifts in day length and solar angles will continue to guide reproductive timing, migration, and growth cycles. Life on Earth, in both terrestrial and marine ecosystems, will continue to track these gradual solar changes, evolving strategies that allow survival in a planet of slowly but persistently shifting conditions. The long-term habitability of Earth will depend on the continued balance of physical, chemical, and biological processes, atmospheric regulation by photosynthetic organisms, oceanic nutrient cycling, tectonic reshaping of continents, and glacial modulation of sea levels will interact to maintain environments suitable for life. Species diversity, evolutionary adaptation, and ecological interactions will ensure that even in the face of extreme climates, tectonic upheavals, and solar intensification, Earth remains a living planet, capable of supporting complex, interconnected ecosystems across continents and oceans. As we reflect on this immense span of time, it becomes clear that the story of Earth millions of years from now is one of slow transformation, resilience, and balance. Continents will shift, oceans will redistribute heat and nutrients, glaciers will sculpt landscapes, and life will continuously adapt to the evolving planetary conditions. Each species, ecosystem, and landscape will participate in a persistent, interwoven dance of adaptation, survival, and renewal, creating a planet that is both familiar in its patterns of life and profoundly transformed in its physical and chemical landscapes. The distant future of Earth is not a static vision, but a dynamic tapestry, where the forces of geology, climate, and biology operate in concert, shaping a world that is simultaneously harsh, fertile, and enduring. Over the next tens of millions of years, Earth's climate will continue to adjust in response to the interplay of solar radiation, atmospheric composition, and oceanic circulation. Polar ice caps will wax and wane, slowly reshaping coastlines and inland waterways. Even small shifts in ice sheet extent will influence global sea levels, creating transient shallow seas over continental margins and exposing new land that can be colonized by plants and animals. River systems will adjust to these changing elevations, depositing sediments in deltas, forming lakes, and sculpting valleys. Over time, these geological and hydrological processes will establish new ecosystems, each subtly different from its predecessors, yet all operating within the constraints imposed by planetary physics and chemistry. Continental interiors will continue to undergo cycles of desertification and occasional rehydration. Wind patterns will transport dust and fine sediments across vast distances, enriching soils far from their source while stripping others of nutrients. Mountain ranges rising from tectonic collision will create rain shadows, concentrating aridity in some regions while enhancing precipitation in others. Organisms within these environments will develop specialized survival strategies, deep-rooted flora accessing subterranean water, animals storing energy and water to endure seasonal scarcity, and microbial communities stabilizing soils and recycling nutrients. Life will persist not because conditions are ideal, but because adaptation will gradually carve viable niches within the extreme landscapes. Coastal ecosystems will remain highly productive and resilient, responding to shifts in sea level and ocean chemistry. Mangrove forests, estuaries, and tidal marshes will act as buffers, mitigating the impact of rising seas while providing habitat complexity that supports a diversity of species. Coral reefs, sensitive to temperature and acidity, will migrate or adapt slowly over time, maintaining their ecological role as nurseries for fish and invertebrates. Ocean currents will continue to transport heat, oxygen, and nutrients across basins, sustaining phytoplankton populations that form the foundation of the marine food web. Even subtle variations in temperature or nutrient distribution will propagate through food chains, gradually shaping evolutionary pressures on larger marine organisms. Volcanic activity, though episodic, will have long-term consequences for planetary climate and ecosystems. Submarine eruptions will build seamounts and islands, while subaerial eruptions will create fertile plains and alter regional topography. The release of gases such as carbon dioxide and sulfur dioxide will influence atmospheric composition, occasionally cooling or warming surface temperatures over extended periods. Lava flows and ash deposits will modify drainage patterns and soil chemistry, creating opportunities for new ecosystems to form while challenging existing ones. Life will respond with adaptation and migration, gradually integrating these disturbances into the broader pattern of ecological resilience. The deep biosphere, largely insulated from surface changes, will continue to harbor life with remarkable stability. Microbial communities in sediments, deep ocean vents, and subsurface rocks will persist with minimal influence from climatic and tectonic shifts. Their metabolic processes will contribute to long-term geochemical cycles, including carbon and sulfur cycling, influencing both local chemistry and broader planetary conditions. Over millions of years, this hidden world will provide continuity, buffering life against the extremes occurring at the surface and maintaining a reservoir of metabolic diversity that can repopulate surface ecosystems when opportunities arise. Nutrient cycles will remain a fundamental driver of ecosystem structure and function. The erosion of mountains, the deposition of sediments, and the decomposition of organic material will recycle elements essential to life. Nitrogen fixation by bacteria and chemical weathering of rocks will replenish nutrients in soils and oceans, sustaining primary productivity. Photosynthetic organisms, both terrestrial and marine, will continue to regulate atmospheric oxygen and carbon dioxide, influencing global climate over geological timescales. These interconnected cycles will ensure that, despite extreme climates or tectonic upheavals, life can continue to thrive, adapt, and diversify. Over long periods, the sun's gradual brightening will impose subtle but persistent pressures on ecosystems. Equatorial regions may experience higher temperatures and intensified precipitation, favoring lush forests and monsoon systems. Mid-latitude zones may oscillate between semi-arid grasslands and temperate forests, guiding the migration and adaptation of plant and animal species. Polar regions, while warming, will retain pockets of glacial ice that serve as refuges for cold-adapted life. Life will continuously track these changes, evolving physiological, behavioral, and ecological strategies to survive within the slowly shifting habitable zones of the planet. Finally, sediments and fossil records will provide a lasting archive of these processes. Layers of rock, enriched by minerals and organic matter, will record glacial advances and retreats, river migrations, volcanic events, and ocean chemistry changes. Fossils will document the gradual evolution of species, capturing forms that emerge, adapt, or vanish. Chemical markers will reveal shifts in atmospheric composition, ocean acidity, and nutrient availability. In this archive, every geological and biological process, no matter how slow or subtle, leaves an imprint, a testament to the resilience, adaptability, and persistence of life over millions of years. The planet's memory, encoded in rock, sediment, and fossil, reflects the quiet but continuous transformation of Earth and the ecosystems that inhabit it. Over millions of years, ecosystems across the globe will reorganize in response to shifting climates, tectonic movements, and gradual solar intensification. In arid continental interiors, deserts will dominate much of the landscape, yet life will persist in niches shaped by water, availability, and soil composition. Plant life will evolve to maximize water efficiency, with deep root systems tapping subterranean aquifers, thick or reflective leaves minimizing evaporation, and the ability to enter dormancy during prolonged dry periods. Herbivorous animals will adapt to sparse vegetation, developing digestive efficiencies and migratory behaviors that track seasonal availability of forage. Predators will follow these patterns, maintaining ecological balance within these extreme but persistent systems. Coastal regions and estuarine zones will continue to serve as centers of productivity and biodiversity. Mangroves and salt marshes will stabilize sediments, protect shorelines, and provide complex habitats for fish, crustaceans, and migratory birds. Coral reef ecosystems will adjust gradually to shifts in ocean temperature, acidity, and nutrient flow, maintaining their ecological function as nurseries and feeding grounds. Sediment deposition from rivers will enrich deltas and coastal plains, supporting dense plant growth and sustaining food webs that connect terrestrial and marine environments. These coastal ecosystems will act as both buffers and connectors, bridging land and sea over evolutionary timescales. Oceanic circulation patterns will persist in shaping marine habitats and influencing global climate. Warm equatorial currents moving toward the poles will distribute heat, while deep ocean currents transport nutrients and dissolved gases to the surface in upwelling zones. These processes will maintain regions of high productivity, supporting diverse communities from microscopic plankton to apex predators. Shifts in seaway configurations caused by tectonic movements will alter current pathways, prompting migration and adaptation among marine species. Over geological time, these slow changes will continually restructure marine food webs, guiding evolutionary pressures without abrupt disruption. Volcanic activity will intermittently modify both terrestrial and oceanic environments. Submarine eruptions will create new islands and seamounts, offering colonization opportunities for marine and avian species, while subaerial eruptions will deposit ash that enriches soils, forms fertile plains, and alters atmospheric composition. Periodic emission of carbon dioxide and sulfur compounds will influence global climate over centuries to millennia, producing subtle cycles of warming and cooling. Life will respond incrementally to these changes, with migration, adaptation, and natural selection continually reshaping ecosystems in ways that are gradual yet persistent. Glacial and polar regions will remain critical refuges for species adapted to cold environments. Ice sheets will expand and retreat according to long-term climatic cycles, carving valleys, depositing moraines, and forming lakes. Microbial life, lichens, and cold-adapted flora will persist along glacial margins, while animals such as small mammals, birds, and fish exploit these habitats for breeding and feeding. These refuges will serve as reservoirs of biodiversity, ensuring continuity even when warmer regions become inhospitable. They will demonstrate how localized environmental stability can buffer global ecological variability and preserve lineages over millions of years. Nutrient cycles will continue to underpin planetary ecosystems. Weathering of rocks and the deposition of organic matter will recycle elements such as carbon, nitrogen, and phosphorus. Photosynthetic organisms will regulate atmospheric oxygen and carbon dioxide, while decomposition and soil processes will return nutrients to terrestrial and marine habitats. These interconnected cycles will sustain primary productivity and enable complex food webs to function even in regions challenged by extreme climates or fluctuating environmental conditions. Over millions of years, this cycling will help maintain the habitability of Earth, allowing life to persist despite constant planetary transformation. The sun's gradual brightening will continue to impose subtle but persistent pressures on global climate and ecosystems. Equatorial zones may become warmer and wetter, supporting lush tropical forests, while mid-latitude regions alternate between semi-arid grasslands and temperate woodlands. Polar zones, retaining glacial ice, will shelter cold-adapted species, maintaining continuity within the biosphere. Seasonal and diurnal cycles will slowly shift over millions of years, influencing reproductive timing, migration, and growth patterns. Life will persist, continuously adjusting to the slow progression of solar energy input, adapting in ways that are measured yet inexorable. Reflecting on these changes, it is evident that Earth millions of years from now will be a planet of subtle transformation and enduring resilience. Continents will continue to drift, reshaping oceans and climates. Glaciers and deserts will expand and contract. Volcanoes will create new landscapes, and oceans will redistribute heat and nutrients. Through it all, life will persist, adapting to the slow but continuous pressures of an evolving world. Each ecosystem, each species, and each geological process will participate in a vast, interwoven cycle of change, illustrating the remarkable capacity of Earth to sustain life across eons. As millions of years pass, the Earth will settle into a slow rhythm of transformation, guided by the interplay of tectonics, climate, oceans, and life. Mountain ranges, continuously uplifted by plate collisions, will gradually erode, depositing sediments that fertilize plains and coastal regions. Rivers will meander, carve valleys, and feed nutrient-rich deltas, sustaining ecosystems in every biome. Deserts will expand and contract, shaping the adaptations of flora and fauna, while intermittent rains and rivers create corridors of life in otherwise arid interiors. These processes, relentless yet gradual, will sculpt landscapes that are both dynamic and enduring. Oceans will remain central to planetary stability. Warm currents moving from the equator to the poles will redistribute heat, moderating climates and supporting the productivity of marine ecosystems. Upwelling zones will continue to deliver nutrients to surface waters, sustaining phytoplankton blooms that form the base of marine food webs. Deep-sea currents will transport dissolved gases and minerals, connecting isolated ecosystems over thousands of kilometers. Even as continents drift and sea levels rise and fall, life in the oceans will persist, adapting to changing habitats and chemical gradients with quiet persistence. Glacial refuges and polar habitats will continue to preserve species during periods of climatic stress. Ice sheets will expand and retreat with glacial cycles, carving the terrain and influencing river and lake formation. Cold-adapted plants, microbes, and animals will persist in these zones, serving as reservoirs of biodiversity. When climates shift, these populations will recolonize other regions, ensuring continuity and resilience across global ecosystems. In this way, even extreme environments will act as lifelines for life, providing stability amidst constant planetary change. Volcanism will leave its mark both subtly and dramatically. Lava flows and ash deposits will create new topography, alter soils, and contribute to long-term chemical cycles. Submarine eruptions will form new islands and seamounts, while eruptions on land will create fertile plains and influence atmospheric composition. These geological processes will continue to challenge life, but also offer new habitats and evolutionary opportunities. Over millions of years, volcanic activity will punctuate the steady rhythm of planetary evolution, reminding us of Earth's capacity for both creation and transformation. The biosphere, in every corner of the planet, will continue its quiet adaptation. Species in deserts, mountains, forests, wetlands, and oceans will evolve in response to environmental pressures, developing traits that allow survival in extreme or fluctuating conditions. Migration patterns, reproductive timing, and physiological adaptations will follow the slow beat of climatic and geological change. Life will persist, not because the environment is static or predictable, but because it is capable of continuous adjustment, demonstrating resilience that spans millions of years. Nutrient cycles and atmospheric regulation will ensure that Earth remains habitable. Weathering, erosion, decomposition, and photosynthesis will recycle essential elements such as carbon, nitrogen, and phosphorus. Oceanic and terrestrial primary productivity will sustain food webs, while photosynthetic organisms will continue to regulate oxygen and carbon dioxide concentrations. These interconnected cycles will maintain global stability, allowing life to persist even in the face of tectonic upheaval, climate variability, and solar brightening. The planet's capacity to self-regulate will provide the framework for long-term ecological continuity. Sedimentary layers, fossil deposits, and chemical signatures will record these processes, creating an archive of Earth's long-term evolution. Glacial moraines, river sediments, volcanic ash layers, and deep-sea deposits will preserve evidence of environmental change, species adaptation, and ecosystem reorganization. Fossilized remains will capture the forms of plants and animals that thrived, migrated, or disappeared, providing a continuous record of life's resilience. Every grain of sediment, every mineral deposit, every fossilized leaf or shell will testify to the slow, persistent transformation of the planet and the life it supports. Reflecting on these immense timescales, it is clear that the Earth millions of years from now will be a world of both profound change and enduring stability. Continents will drift, shaping climates and oceans. Glaciers will carve landscapes, deserts will expand and contract, and volcanic forces will reshape regions. Ocean currents and nutrient cycles will maintain the rhythms of life, while atmospheric and solar changes will impose slow but persistent pressures. Through all of this, life will persist, continuously adapting, evolving, and finding niches in every environment. The distant future of Earth is not static. It is a dynamic, interconnected system in which geology, climate, and biology operate together in harmony over the span of eons. As we close our contemplation of this distant future, there is a quiet beauty in the knowledge of continuity amidst transformation. Each ecosystem, Each organism, each river, mountain, and ocean current plays a role in maintaining the balance of life on Earth. The planet's story is one of resilience and adaptation, a testament to the capacity of life to endure over incomprehensible spans of time. In this vast, slowly evolving tapestry, Earth's distant future offers a serene reflection, a world of constant motion, persistent cycles, and enduring life, quietly unfolding in harmony with the rhythms of the cosmos.